Welcome back. You are watching the Boiler Analyst YouTube channel, and we are discussing hydrogen embrittlement problem, which is a very damaging, devastating tube failure mechanism. In the first part, I have discussed about the causes or the damage mechanism itself, how it happens, and I have mentioned that there are two parts in this. One is the corrosion, other is the overheating, which both are there. Then it may lead to a problem like hydrogen embrittlement, right? And I told you what are the possible way of controlling it, what are the possible uh, correction measure in hydrogen embrittlement. And the third part, I was talking about a case study which I am sharing in this part too, right? Uh, this case study is on a typical problem of hydrogen embrittlement which is faced by me, which is experienced by me. There was a system where this problem was occurring and I was invited to solve it. So in this part, in this case study, I'm going to show you uh, exactly how I have reached to the conclusion that what are the root causes of this problem and what are the precautionary measures that I have taken. It's possible that I may be able to share the findings and the analysis with you in this part, and I may have to create another video with part 3 where I'm going to share you that what are the corrective measures that I have asked them to take care, right? So this is a case study on a bi-drum utility boiler. You understand bi-drum, that is having a steam drum and a mud drum with a bank tube, 3-pass boilers. It was a 270 tons per hour design capacity boiler. So it was a cogen CPP boiler, captive power plant boiler, and it was having two stage of superators, one economizer, one rotary air preheater, and with a dual fuel firing system. So both gas and oil with separate burners. It's not that in one single burner gas and oil. So there are gas burners and oil burners. So it can fire with both gas and oil condition. Where it has taken place? It has taken place in the water walls. I told you it is a typically water wall problem in the water walls. The rear water wall. So it was a front wall fired boiler. The burners were located on the front wall. But the rear water wall side, the problem occurred. And the metallurgy, as you can see, is SA192, which is carbon steel. The pressure of the boiler was 108 kg per centimeter square, and the temperature, superheated steam temperature, was 510 degrees centigrade, and it was 8 years old boiler. Now, when I was invited here, they were facing multiple failure problem, typical this kind of hydrogen embrittlement, what we have seen, this kind of problem since 2020. In fact, I went there in February 2023, and since November to that time, in one of their boiler, they have faced three failures almost back to back. In fact, on 2nd February, there was a failure and the boiler was stopped. So when I went there, one of the boiler was stopped, right? And this are typically having the kind of look is a hydrogen embrittlement window pocket type opening. When I checked the failed components, I found a lot of indication of corrosion, blister formation on the OD side. Now let me tell you, whenever there is a blister formation on the OD side, always cut the tube and look from the inside. You are going to find there is a corrosion uh, pocket there, right? So wherever is a small area, the corrosion thins the material, right? With pressure inside, it is going to form a blister type of thing, right? So inside, if you can see, you could see clear indication of corrosion, and it's a gouging type of corrosion, right? Some more sample which I checked, it was showing corrosion gouging, and in one of the tube component, it was a clear indication that there is a strip type of thing, and this is on the 12 o'clock position to facing the fire side, a strip type of corrosion area, which is a clear indication of film balling, that has taken place in the system, right? Once the film boiling taking place and the steam blanketing is taking place, it is almost forming a two parallel line type of strip, and it is almost a signature of a film boiling condition. And corrosion is indicated there, right? Now, these people, they have carried out, by the time I went there, they have carried out all the metallurgical study of these failures, because this has been happening since 2020 and multiple occurrence was there, right? They must have faced around 10 to 12 such failures. So they have conducted the metallographic study by two reputed organizations. So microstructures and everything was there. Identification of the damage mechanism as hydrogen embrittlement was already there. They have conducted, interestingly, they have conducted a deposit analysis, both EDS and XRD analysis, and they have conducted a thorough study of their boiler water chemistry. These are all by the reputed parties. By the time I went there, all these reports were available to me. I knew the problem is damage mechanism is hydrogen embrittlement, right? There is no doubt about it. Now, if you see the microstructures are very evident. I told you in the first part that these micro cracks in the grain boundaries, right? If you magnify this, typical micro cracks in the grain boundaries are almost a signature of hydrogen embrittlement cracks. You don't need to be a trained metallurgist to understand this. Some more microstructure was also indicating the same thing. All these failures are because of hydrogen embrittlement. And the deposit analysis which they have carried out, that too, right? Now, the failure, one of this failure, if you take a look at this, it is a typical window type of opening with a brittle edge, right? Which is again a clear indication of hydrogen embrittlement problem. Okay, so hydrogen embrittlement problem was confirmed. There is no doubt about it. Now, I have to look for an indication of two things. One is how the corrosion is occurring. What kind of corrosion is occurring? Because I told you there are two corrosions that can lead to hydrogen embrittlement problem, and that is caustic corrosion, gouging corrosion, as well as acid chloride corrosion. And there has to be some overheating condition. So if you see the deposit analysis, that is the EDS, energy dispersive spectroscopic analysis, there you could see the indication of copper and zinc. Now, I told you that copper and zinc are two highly conductive metals. And if there are deposits of this conductive metal, it is definitely going to create a very strong galvanic cell in the system where corrosion will definitely occur. And wherever corrosion occurs, there will be deposits, then there is a chance of under deposit corrosion. We have already seen the film boiling indications. So below the film boiling, so corrosions can occur. There is no doubt about it. But the question is, from where the copper and zinc are coming? Usually in power plant boiler condenser, you get the metallurgy admirative brass. Admirative brass is nothing but copper and zinc. But when I talked to them, they said that their CPP boiler condenser, that is the turbine condenser, it is having stainless steel metallurgy. So from where the copper and zinc are coming? That is the first question. Okay. Now, when I check the other test, that is the XRD analysis of the deposits, where you actually get the compound of the deposit inside the deposit, the components of the deposit, then the two things are there. One is again the indication of copper corrosion metallurgy or corrosion product has come into the system and getting deposited. This is typically the copper corrosion products, the cupric oxide and the iron copper component. These are all copper corrosion products. Now, from somewhere, some copper metallurgy is getting corroded, and that product is getting included in the system. It is getting carried over to the system. That is the first indication. Second thing, if you see here, sodium ferrite was one of the compound, caustic was another compound. So now we do not have any doubt what has caused the corrosion. It was a caustic gouging corrosion, right? Sodium ferrite, sodium ferrate, these are the two compounds from from the caustic gouging corrosion reaction. And the third thing I have noticed that they are also showing the calcium carbonate and calcium oxide in the deposit. Now, calcium, magnesium, these are called hardness. And in boiler system, in boiler water treatment, hardness is always maintained nil, right? If hardness is at all coming, then there is a possibility that the hardness is coming from somewhere else, not from the treated water. So I need to find out the location from where this hardness is coming, where the copper and zinc is coming. And if calcium is coming to the system, there will be deposit, there is no doubt about it. And there will be deposit. Below the deposit, there is a chance of, again, corrosion, and particularly with the conductive metal present, there is a highly strong probability of corrosion in the system. Okay. So what we have done is I have discussed with all the O&M group people, right? I wanted to know their findings, their experience, and basically the history of the system. What has gone wrong in the system at any point of time? What they are feeling, what they have found, right? I talked to the inspection people. I talked to the uh, chemistry department, their DM department, right? And when we discuss in detail, right, that time all these things, the indications that what could be the problem, they actually surfaces, right? So after discussing with these people, all these O&M guys, I'm going to share what are my findings. The first thing I came to know from these operation people that okay, these boilers were 270 tons per hour boiler, right, with a maximum capacity of 291. Right from the beginning, they never could generate more than 240 tons per hour. Even when they are trying to generate 230, 240 tons per hour, the furnace pressure is almost reaching to the high alarm level furnace pressure, right? I asked them that whether OEM has conducted the performance guarantee test. They said that no performance guarantee test was conducted on these boilers, right? They have conducted some kind of a assurance test or something like that, right? And at that time, it was taken to very their promised capacity of 270 tons per hour, but the furnace pressure was very high at that time. So they are never able to operate this at more than that. Now, whenever such kind of a situation is there, then my boiler is not able to generate the design capacity of steam, right? There is always a possibility of overheating. Why? Because since my boiler is 270 ton per hour boiler, I will always try to generate 270 ton per hour. If the boiler is not having the capacity, ultimately it is going to lead to the overheating situation. That is the first doubt I had. Okay. Now, the second thing is that they have cut down the load to, since they have four boilers, so they are managing with all these four boilers together, and they are limiting the load to 170 ton per hour. I told you the reason, because when they go to the maximum capacity of 230 to 40 tons, then the furnace pressure goes very high, and the flame also becomes very erratic at that time, right? And they are having this 8 burner operation. So two rows of burner, four each, and they were operating with both FO and FG, 4FO, 4FG, fuel gas. That is, this is the refinery gas basically, almost like natural gas with a little higher calorific value. Okay. Now, uh, this they have tried with various uh, uh, configuration with the alternate FG, FO, FG, FO like that, top row FG, bottom row FO. But they want to keep one thing there, that the farthest two end burners, they would prefer to keep the FO because that flame can be seen. The BFG flame cannot be seen from the side panel peephole, right? So that is something they always prefer. The next thing I found is the attenuation spray at even such load of 170 tons per hour, right? It was coming to 20 tons per hour. I checked with their OEM technical specs and the guaranteed parameters, then I found that the at partial load of 60%, the temperature spray was 4 tons per hour. So it was already very high a temperature spray. Now that creates another problem. It is not only the water wall issues. If a temperature spray is so high, that means superheating heaters are also getting a very high amount of heat. And if the superheater has not failed now, it is going to fail very soon. Because such kind of an overheating, if it continues, then if not short-term overheating, you are definitely going to face a long-term overheating problem in the coming years. It's already 8 years old boiler, right? That is another finding we have. When I checked from the side panel pip hole, I found that the flame was totally erratic, right? It was scattered flame and it was very long. And at times it is almost touching the rear water wall, right? So clear indication of flame impingement can be seen physically. When I asked them, they said that, sir, if you see the 230 load condition, at that time the flame is always touching the rear water wall, right? So they are getting a very concentrated heat flux on the rear water wall, and that is clearly indicating why overheating is there, right? So I found the overheating cause here. Now, from the peephole, which is located at the top, from where you can actually see the bottom of the superheater, there, when you take a look from the peephole, you should not see anything. It should be totally dark. Why? But because the burner elevation is completed quite a far below, and flame should not come there. But I could see the indication of flame even at that elevation, and that was telling me that the delayed combustion is prevailing in the system, right? Which is answering why that high temperature spray is resulting in the system. So there is a definite cause of a superheater failure in the future, and that is because of delayed combustion also, right? Now, if there is combustion problem, then the first question comes whether the burner is properly tuned or not for combustion. So when I asked them that whether you have tuned the burner, when the last time you have tuned the burner, they said that at the time of the commissioning, whatever the OEM has done after that, we have not touched. There was a damper, uh, which was actually a primary damper. Since the boiler was stopped at the time, I went inside and checked that if I move this damper, then there is a sleeve and there is a slotted, cylindrical portion at the core of uh, the burner, and this sleeve is moving over the slots and opening the slots one after another. If it goes up and down, uh, moves front and back over the burner shaft. So that was basically the primary air control. If I checked with the rotation, if I rotate it clockwise with two pitch of rotation, the slot, the number of slot which was closing was 10%, right? So it was closing with an clockwise movement. I asked them that when you have operated this damper, they said never touched the damper at any point of time. Okay, so that is another problem, that combustion was not due, and since the flame was scattered and long, so naturally another doubt is coming, because these are FO flame which you can see, then whether there is a problem with the atomization, or with the some amount of dirt that is coming with the fuel, or whether water is coming with the fuel, right? So I checked first of all their storage tank. Right from the boiler, I went to their storage tank and I checked this storage tank. They have two storage tanks, where the refinery, they are getting the FO directly from the refinery, and these two storage tanks were last cleaned at the time of commissioning. That means there was no cleaning done after that, right? So no cleaning in the FO tank, that would definitely suggest that there is a high accumulation of sludge in the FO tank, because FO comes with a high amount of contamination, solid contamination, right? For 8 years, it has not been cleaned. So if there is a high deposition of sludge, there is always a possibility of this sludge getting carried over. Now, which if you feel that it is going to be taken care of by the oil filter, by the strainer, discharge strainer, that would be a wrong idea. If the discharge strainer go on getting accumulated, right? So there can be a possibility of carryover if it is not cleaned on the regular basis, right? So when I checked with there that what is the process of oil, water removal from the tank, they are doing it once in a shift, and actually once in a 3 shift, right? So they just open the valve when the water comes, immediately close the valve and done. FO has got a strong possibility of water contamination, and if water comes with the flame, it will always, scatter the flame. If I describe the flame was like going up and sometimes coming down, so it was very erratic flame. This is a strong indication of water contamination in the FO. Okay, the discharge filter, which is a duplet filter, they're cleaning on the basis of DP, and that is done at many places. But a good practice is always clean the filter once in a week, because it's a duplet filter, so the operation is not going to be hampered because of this, right? But they have been doing it on the basis of DP, and when I asked that when the DP comes, they said sometimes even 6 months the DP is not reaching. So there is an accumulation of dirt, and there is always a chance of carryover of this dirt. And when these dirts come to the burner and partially clogs the burner, the flame gets scattered. Okay. Now, if you see the feed water supply network, because I have to find out from where the copper, zinc, the hardness, these are coming. Now, if you see the feed water supply network, they are getting the feed water from a condensate storage tank, CST. Now, this CST is getting the water from various places. So one is the CPP hot well that is coming, condensate is coming back directly, right? And since it's a stainless steel metallurgy, so that is not a problem. Then they are getting makeup done in the CST from the DM plant, and they are getting some water coming from the process which they call the suspect condensate, and the suspect condensate are always coming through a condensate polishing unit, so it is getting treated. What they call suspect condensate? So in a process heat exchanger, wherever the process side pressure is more than the steam side pressure, that condensate is suspect condensate, because if there is a leakage, then the steam will get a process contamination. So what they do, they bring it through a CPP. So fine, this is not a problem. Now this CPP steam is not just going to the turbine, it is going to various processes, right? So there are 6 different process plants from where the steam is going from the CPP, and all this process plant is giving the condensate back. Some of these plants are having process heat exchangers from where the condensate is coming back. Now they call it pure condensate. Why? Because in this process heat exchanger, unlike the suspect condensate, the steam side pressure is more than the process side pressure. Therefore, there is no chance of process contamination if there is a leakage. But if there is a corrosion, then the corrosion product can come, right? And 4 of these process plant are having some condenser, surface condenser. Actually, they were having steam-driven compressors, steam-driven pumps, and which are going to ultimately condenser. So this surface condenser condensate is again coming back to the system. Some part of this is going to the export deaerator and subsequently different process, and some part is coming back, a major part is coming back to the CST. So naturally, it is not just the CPP condensate that is coming to the back to the system. It is from all this process system. So I asked them to give me the metallurgy of this, all the surface condensers, and then I found 3 of this plant surface condensers are having admixture brass in their condenser. Now I know from where the copper and zinc is coming. Okay, admixture brass is 70-30 copper and zinc. So if there is a corrosion, that corrosion product can come back to the system. There is no protection in there, and not only that, the cooling water contamination can also take place. Therefore, hardness can also come from the system. Fluoride can come from the system. So there's not just the threat of caustic corrosion, there is a threat of fluoride corrosion also in the system. Now, this happens to be the root cause of the corrosion problem, right? This particular contamination is the root cause of the corrosion problem. I have studied the water chemistry there. The water chemistry, the makeup water DM, there is MB outlet, was having a conductivity of around 0.2 to 0.3, or almost 0.3, which is not good, right? Your MB outlet conductivity has to be less than 0.2 microsieverts per centimeter. Their pH MB outlet pH was 7.5 to 7.7, which is very, very high. MB outlet pH is usually in the range of around 6.8, 6.9. In this case, we were getting 7.5, 7.7, right? It's a clear indication of some kind of a slippage is there, right? And most probably sodium slippage. So when I check the the water analysis that have been done by NALCO actually, right? The sodium in the DM water was very, very high, 153.17 ppb. That is a very high sodium, right? So there is some problem in the MB also. That is not safe. And if such kind of sodium comes in the system, the drum water pH will be always on the higher side, right? In fact, when I checked the drum water pH in one particular day, I found that drum water pH is going to 9.8. But I told you in the first part that even 9.8 is not considered high. Why? Because the limit is 9.2 to 9.8. So 9.8 is still within the limit, right? But that high pH shows that there is an ionic imbalance in the system, right? And if there is a concentration increasing mechanism like below a deposit, below a film boiling, then it will definitely lead to a gouging corrosion because free caustic will form, right? And amine is dosed for pH boosting. So whatever DM water they're getting, they're dosing amine. Amine is not a problem. Amine will ultimately give some ammonia in the steam, right? And if this steam is going to the CPP condenser, no issue because that is stainless steel metallurgy. But unfortunately, this steam is going to those processes also. And wherever there is a copper metallurgy, the steam ammonia has to be limited. Otherwise, it becomes very corrosive, right? Copper corrosion cannot be avoided there. Steam ammonia has to be controlled less than 0.5 ppm in such cases wherever there is a copper metallurgy. And what they have been doing, they have been continuously keeping the CVD open. When you keep the CVD continuously open, it becomes very difficult to actually control the water chemistry and maintain a balanced water chemistry. So all these problems are suggesting that water could be the root cause, right? So I'm going to conclude here because if I continue with the corrective measures, the video is going to become very long. New people will not have that much time to watch the video at a one go. So I am going to create another video, part 3 of this section, where I am going to discuss about the conclusion part, the analysis part, and the corrective measures that I have suggested them, right? Afterwards, the problem was resolved. So with that, I am going to conclude this session. Please comment on this video in the comment section. In fact, I would invite your suggestions there. I have already given you all the facts, all my findings over there. I have also analyzed what could be the problem, right? What is the scenario there? Kindly suggest that what should be the correction method here. Because in the next video, I am going to share with those suggestions that I have given them for the correction method and which actually help them, right? Do not forget to subscribe to the channel to get the notification of my subsequent videos whenever I upload it. And thank you and bye bye.